Hey guys, welcome back to the second project on convolutional neural network. Here we'll be showing you how convolutional neural network works with the image of a cat and a dog. We're trying to use convolutional neural network to perform a classification task on cats and dog. So we'll still be using the same architecture as the one we use for MNIST datasets for number classification in our previous video. If you've not watched it, please try to refer to it. There are some vital information that will help you in understanding this video. So we'll be following some architecture and we've explained the architecture usage. All we have to do is to start importing our model. Firstly, we will need a numpy for manipulation of numbers. We are doing normalization, so at the point of normalization, we'll be needing numpy for normalization. Then we import a matplotlib to view our images at some point when we need to. Next, we'll need our model and our layers in TensorFlow. So we're importing sequential. Sequential will be sequential just like a stack. Next, from TensorFlow .keras .layers import. Here we'll be importing things we need for the convolutional neural network for the model to work. So we need the convolutional 2D. We need the max pooling layer. Pooling of 2D. We need our flattening layer, of course. We need our dense layer. We don't necessarily need dropout here, so and that's all for what we need to import for now. If there's any other thing we have to import, we'll be bringing them here one after the other. The dataset we use in this project is linked in our description. Do what to download it if you want to practice what is down here. So to import our module, we need the input for the X-train. X-train, firstly this is our X-train, our input value. So to avoid giving ourselves problem, let's add the delimiter so that we wouldn't be having comma separated issue or any issue relating to delimiters. Great. I think there's an issue. Okay, delimiters is equals to. So next, let's bring in our X train. X tests. That will be input text.csv. So that's the difference between them. Then we'll bring in our label, our target variables, or let's say our label. So white train np, which is numpy, we're going to load our data. np.txt, we're bringing in our main label class. Next, we'll be needing our white tests. The difference between that and this is just test. Yeah, underscore tests, then labels underscore test to CSV. Okay, our delimiter is still active. Oh, our delimiter is not active, so we include delimiter. Add delimiter. We add delimiter as well at this point. Great. So once our data is imported correctly, we use the right directories and every other thing, we will not be having problem with the data set. Next, the next thing we have to do now is to perform a data preprocessing. All the activity we are doing here are still the basics, because this particular section, the first two projects are meant for actual beginners, like they're meant for beginners. So next, what we have is we'll be doing exploratory data analysis. before data processing. At this particular point, we'll be trying confirming if our data is balanced, and if it's not balanced, we balance it by doing data augmentation. The augmentation is the process of trying to balance data you are that's something the one that is having much data. So any of the two approach you are going for is what data augmentation is all about. It is what data augmentation is all about. So let's check for the length of our data points. So let's say extreme shape, great. Not shape, we look for the length. More data in extreme. So let's save our time. So we see we have 2000 in extreme. Let's test. Okay, so we realize we have a relatively balanced data. We have X train, Y train. We have a data that is actually balanced. So here we don't have a lot of problem to do. Although we could actually like try to increase the number of, but since it's more than 1000, I think it's still fair enough for us to get a very valid or accurate result with deep learning, because deep learning quite requires a large numbers of data. Anyway, by the way, convolutional neural network is data a type of deep learning neural networks. So next we'll be doing data preprocessing. Here we'll be looking at the shape of the data and the image channel. If the image is having 2D channel, 3D channel, or 1D channel, that's what we want to take into consideration here. So putting the shape of the data, X. So let's try visualize the shape of the data. Okay, so we've seen the shape of data we're having, and for our neural network to be able to process the information we are trying to work on, we need to make it a 3D image, and adding a channel to it. Here we'll be making the channel a 3 because we want to use RGB this time around, compared to what we used earlier in our MNIST dataset, where we use a 1D channel, which is in gray format. So to reshape our image here in data processing, we have to perform two things. Firstly, we do data normalization, where we actually increase the size of the data from large RGB values into a smaller value for easier computation. We reshape the size into a dimension that is easily computable or processed by our neural network. So let's perform the data processing here. That's xtrain dot reshape. So after we've shaped it, this time around we're using only by 100 image, not a very. Then our channel here is 3. The reason why our channel here is 3 is because we are using RGB. RGB we are using a grayscale format image. We'll be using a channel of 1. So we're using a channel of 3 here because it's RGB 3. So next, do the same thing for our text data sets. Great. So here we've been able to perform the reshaping. We need to normalize the data because obviously data will be in the range of 0 to 255 because the highest value of RGB is 255. So we're trying to reduce the value of the shape of the data from a larger data set into a smaller one. So to reduce that, we divide it by 225 because the highest RGB value is 255, obviously. And we're trying to make sure that the value we are going to attain here will be in a floating format. In as such, the value we're using to divide it will be 0.0. Let's see. That's extreme. We've been able to process our data, we're able to perform data normalization. Let's see how our data looks like. Let's see the type of data we're having firstly. So here we'll try to bring a random image. Let me see, okay, let me see img. I need a random image. Let me use a random image here. I need something like a random dot one int. So I'll have to import my random here because I'm obviously using a random value. From 0 to range of all values I have. There's x string. So obviously -1 because I'm starting from 0 for the indexing. Next, let me display the image. So I'm displaying the image here like this. Then I will add the comma here to consider all image. Import random. That's the next thing. because I'm using random here. Okay. And our neural network is still trying to manipulate it and reduce the quality. That's why we have this particular type of image. But when it be that
We've been
we do
able to
not
see
like
how
reduce the
our
size by
image
doing
or
normalization, we'll
what
still be
our
having our
image
clearer
looks
image.
like
So let's go. Next we'll build our
because we are
model.
using an RGB.
Building our model will start with the name of the model, the name we want using, defining the model. Then we'll use sequential to create a stack. Sequential is just like a stack that holds all our functions. So here we are using convolutional layer with imported convolutional layer. We are using convolutional layer of 2. You have to define your feature map yourself. So here I'm using 32. Then next is my kernel, because my kernel will be used to actually convolve my convolutional layer at first instance before I do a max pooling layer. So which size of max pooling layer do I want to use? I want to use a 3x3 of kernel. Rather, I want to use a kernel of 3x3. Then activation function, I want to use value. Why am I using value? Because I want to shunt all values that are negative, like all negative values from the data, because most of the time when we're working with data that are negative, it gives the model issue at times. So here our input shape is 100 by 100 by 3. Why we have 100 by 100 by 3? It is what we define here that we are using. So it's not as if we are coming up with a custom number. So next we will bring in our max pooling layer. So in our max pooling layer, we're using a 3x3 filter of max pooling layer. So we are not using a stride. So, and if you're not using a stride, what happens is the convolutional neural network adopts a default stride and a default padding. So the default stride in the sense that instead of moving in a custom dimension, it will be moving one by one. Next, we define the second convolutional layer, because in our architecture that we're following here, we are using 2 convolutional layer and 2 fully connected layer. So convolutional of 2D. My feature map I'm starting is 32. Then I'm using a kernel of 3x3. 3x3. Activation function is still value. Remember, activation function value is actually shunting non-positive numbers. So next I'll be bringing in my max pooling layers in order to select the most important features. So here my filter for max pooling layer is 3x3. There's a mistake here, 2D. So there's a need for comma at every point. Now if we are through with the convolutional and max pooling layer segment. Let's see. Now we're left with the fully connected layers. So in the fully connected layers, we use before fully connected layers, we should be having a flattening layer. Let's see. Yeah, we have a flattening layer here. So first we'll bring in our flattening layer in order to line up the values we have in an horizontal manner. So flatten and dense. Here we are bringing our fully connected layers now. So the first fully connected layer, what I'll be having will be 64. Trying to list all possible values, all possible outcomes. Then I use that activation function of relu at the same times. Why am I using relu? Once again, is to shunt all non-positive numbers, all negative values, not non-positive, because 0 is part of the value that value is accommodating. So we're done with the first fully connected layer with value. The second fully connected layer, we'll be having our output of 1, because we're having a single class of results. Then activation function here will be sigmoid. The other time we use softmax. Yeah, sigmoid gives similar result as softmax. Here, sigmoid is best for classification of 2 categories. When you're dealing with classification that has to do with is either a dog or a cat, is either a yes or a no. Sigmoid is the best go-to result. So now we are done with our model building. Okay, the model is loading. Do not pass. Yeah, this is a similar. Oh, let's see what the problem is. Keyword unrecognized in argument passed to the next layer. Activation. Let's see. Okay, it's activation, not activation. Yeah, we're done. Good. So the model has run successfully. Now here we will try to compile our model. In model compilation, there are 3 important features. One is your loss, second is optimizer, and the last one is your metrics. The loss is the measure of uncertainty. Take for instance, you're having a fair coin of 50-50 results. Here in 50-50, you are not sure, you're not certain what will actually be the result. Is that a head or a tail? Because it is not certain, probably the next image is bringing is a cat or is a dog. So what you do in this sense is you are giving it a fair loss. Next, you have Adam Optimizer. Adam Optimizer improves the model accuracy. In what sense? It uses 2 important features. Firstly is your momentum, while the second one is RMS propag. Momentum help you prevent the model from getting stuck or being delayed at some point. While your RMS propag, which stands for root mean square propagation, it prevents the model from getting too fast. From getting too fast, it will not miss important features. But if we have a case where the model is too fast, it will be missing some important features. Let's take a scenario of max plane layer, for instance. Our max plane layer, at the point of it selecting its most important features, if for instance we're having a mathematical error or something, let's say we are bringing human being into play now. We're having a mathematical error of maybe decimal point position at the wrong place, and the feature there is actually low. If you don't have a system that is actually very calm, it will rush to pick a particular value, thereby skewing away from the most important features in that particular segment. So RMS propag helps you prevent the model from getting too fast excessively. Let's define our loss. Our loss here is binary. We'll be using a binary classification, which is binary cost entropy. Binary cost entropy. Then our optimizer, we are using Adams. Okay. Yeah, we're obviously using what we have here. So great. So next we'll be fitting our model. Here we'll be training our model.train. Fit what? So how many epochs? Here we're training it on, let's say 5 epochs. Let's train on 5 epochs to save our time. If need be, we will train it again. So as our model is training, let's find the summary of the model. Let's see if the architecture we're having here meets the same architecture we have initially. So together we'll do model to summary in order to view our architecture. So once the epoch is finished loading, we would do that. Then still waiting on the model to load, let's try to create an avenue to evaluate our model. Okay, the model is still loading. So to evaluate our model, we want to get two features, the test loss and the test accuracy. So test loss, test accuracy is equals to model.evaluate. So we're bringing our unseen data here, our x test and y test. I want to point the result of our accuracy. I think, okay, let's see the overall performance of the model. You see we have 76.7 accuracy. Let's retrain it. So to retrain it and continue from where we stop, we have to reload the compile model so as to save or update the model. Okay, model accuracy, model overall accuracy. So you'll be having test accuracy. Okay. Okay, so our model is loading. Let's pause for now and wait for a better result. Or it seems the model is getting to an end anyway. It's becoming endless. Okay, we'll get to the root of the matter soon. Okay, we're having 83.05. So I'm sure on training it for the last time, we'll be having something 90 something percent accuracy. So let's retrain the model again. Now we'll have to pause the video. Okay, welcome back. I think we're having a quite modest accuracy now, 98%. But remember, before you resume model training, you have to start from compile model. So let's see the model accuracy. So in overall, we're having a 7 something. So we just have to go train the model properly. That's the major. Okay, let's see our model summary. Let's see if we're actually following the same architecture as defined in the first instance. So it's going to take a while. So I have this short code to actually experiment what our model is all about. Before experimenting, we have to save our model. So that's our model.save. Cat dog model. Hot dog but Keras. This is the Keras. Okay, so this is the code I'll be using to run the program, but I will explain that when we get to object detection. So I've said the model. The model is still loading. The model summary is still loading. It's taking a lot of time. I don't think we can wait for it. Okay, I think there's something more. Yeah, good. So if we look at the model summary we're having two convolutional layer, one flattened layer, and two fully connected layer. The first fully connected layer is for our normal value where we bring out the whole image as being flattened. Then the second one is the output fully connected layer where we use binary, where we use sigmoid instead of softmax. I remember. Okay, so here let's bring in our model. The model will save here as Keras, but solely one of the advantage you have in here is that the model will save is the same working directory as this file, so we don't have to add any extension or anything. It's kind of let's say intriguing how convolutional neural network works, even computer vision in general, where if you know one, you can work on the rest. So you can see that we're having cats being detected. Okay, yeah, so we have the result now as dog at high percentage. So we are very sure, there's high confidence that okay, this is a dog. Next, we'll be working on the brain tumor classifications system using convolutional neural network. Here we test different MIR scans in order to classify if a patient is having brain tumor or a patient is not having a brain tumor. And in that particular section that we're having next, we'll be going on an advanced level project where we apply the complete workflow of deep learning in solving the problem. Thank you once again, and thank you for joining me.